Okay, so in the last video we gave the definition you see in red here for the cross product in R3, and then we saw how we can use determinants to compute cross products. Okay, so in this video we're going to look at why this definition actually gives us something useful. Okay, and so for that we're going to turn to the geometry of the cross product. Okay, so as we noted in the last video, the cross product of two vectors is itself a vector quantity. So if I want to describe this cross product vector, I need to know its direction and I need to know its magnitude. So let's go ahead and start with the direction of the cross product vector. And I say here in blue, the cross product A cross B is orthogonal to both A and B, and its direction follows what's called the right-hand rule. Okay, so I have my two vectors A and B here, and this plane that I've drawn in purple, this is the plane that contains both of these vectors A and B. Now, if I just tell you that A cross B is orthogonal to both A and B, okay, well, in particular, that would imply that A cross B is orthogonal to this plane. But see, that doesn't really single out what direction A cross B points in, right? Because the vector could point up and be orthogonal to the plane, but it also could point down and still be orthogonal to the plane. So that's where this whole right-hand rule comes in. Okay, so what does it say? It says that if you hold up your right hand and you point your index finger in the direction of A, which is the first vector in the product, and then you point your middle finger in the direction of B, which is the second vector in the product, then your thumb will point in the direction of the cross product vector. Okay, so in this figure right here, we have A here, so I'm going to point my index finger along red. And then we have B here, so I point my middle finger along green. So then my thumb will point upwards in the direction of the blue cross product vector. Okay, so now what if I were to reverse the order of the vectors in the product? Well, there you have to think about placing your index finger along green, right, along B, then your middle finger along red, right, along A. And it's a little hard to show you this when we're not meeting in person, and I can go over this more in our Zoom meetings, but if you imagine doing that, right, so index finger along green, middle finger along red, you're really going to have to turn your right hand upside down, and in this case, your thumb's going to be pointing downwards. Okay, so as a consequence of this, if you reverse the order of the vectors in the product, and you look at B cross A, this in fact is the opposite of the vector A cross B. So this yellow vector B cross A, it's still orthogonal to this plane, but it has the opposite direction of the blue vector A cross B. Okay, cool. So now let's go ahead and turn to the magnitude of the cross product vector. So we have this theorem here that looks very similar to our main result on dot products. It says that the magnitude of A cross B is equal to the product of the magnitudes of A and B times the sine of the angle between the vectors, theta. Okay, now I've gone ahead and drawn our vectors A and B here, and here's our cross product vector following this right-hand rule. Okay, I've also included this vector in red, which is just A translated, and this vector in green, which is just B translated. So in other words, I'm looking at this parallelogram formed by the vectors A and B. And the reason why I'm doing that is that this expression you see on the right-hand side of our theorem, so magnitude A times magnitude B times sine theta, that's equal to the area of the parallelogram formed by A and B. So in other words, the length of our blue cross product vector is equal to this blue area of the parallelogram formed by those two vectors. So why is that the case? Well, I'm going to go ahead and drop this altitude here. Right, this is the height of our parallelogram, and the area of a parallelogram, that's just the height times the length of the base. So what's the length of the base? Well, that's just the magnitude of A, and that's right there. What's the height? Well, if we consider this right triangle right here, the height, right, is the side opposite this angle theta. So if I use the sine of theta is the height divided by the hypotenuse, which is the length of B. So put another way, the height is the magnitude of b times the sine of theta. And this expression is what we see up here. So again, the length of the cross product vector is equal to the area of the parallelogram formed by the vectors a and b. All right, cool. So now let's go ahead and look at some key properties of the cross product, and some of these we've already gone over. So first property says that if you compare b cross a and a cross b, well, they're not equal in this case. They're actually opposites of each other. So reversing the order of the vectors in the product introduces this sign change. They have opposite directions, and that's a result of the right-hand rule convention, okay? And some people call this an anti-commutative product. All right, the next property, right, this is just really the result of that theorem we just stated about magnitude. It says the magnitude of the cross product, a cross b, is the product of the magnitudes of a and b times the sine of theta, and this is equal to the area of the parallelogram formed by a and b. Okay, the third property says that a cross b is orthogonal to both of the vectors a and b, or put another way, a cross b is orthogonal to the plane that contains both of the vectors a and b. Okay, now for the fourth property, when is the cross product 0? Well, this is going to happen when the two vectors are parallel, or in other words, one is a scalar multiple of the other. Okay, so if I consider two parallel vectors like you see here, okay, what's the area of the parallelogram formed by these two vectors? Well, they actually don't form a parallelogram, right, because they lie along a common line. So the parallelogram in this case has 0 area, implying that the magnitude of the cross product vector is 0. And so we have our result. Now, in particular, any vector is parallel to itself, right? So if I take any vector a and I cross it with itself, I will get the 0 vector. All right, and then these last two properties, pretty similar to what we saw with the dot product. Okay, so the cross product is distributive. So if I have a cross the sum of two vectors, b and c, I can go ahead and distribute the vector a, and here the multiplication is the cross product, so a cross b plus a cross c. And then this last property says that if I have a cross a scalar multiple of b, I can just take this scalar out front, and I have s times this cross product of a and b. All right, well, that's going to do it for this video. In the next couple of videos, we're going to look at more examples illustrating the cross product. All right, thanks.